Professor Roshankarana Singha, the Professor of Climate Change Impacts and Coastal Risk, AXA Chair in Climate Change Impacts and Coastal Risk, IHE Delft Institute for Water Education, Netherlands. So, Professor Dr. Roshankarana Singha is a senior specialist in resilient ports of course at deltas and honorary professor at the University of Melbourne, Australia. He holds a Bachelor of Science Engineering at first class honours from University of Peradeniya, Sri Lanka. PhD Coastal Engineering and Oceanography from the University of Western Australia, with over 200 peer-reviewed articles, including 15 plus Nature journals, and Renew expert in adaptation to climate change and coastal zone management. He has supervised and co-supervised 10 plus postdoctoral fellows and 25 plus PhD candidates and numerous MSc students. And he has led capacity development projects across Asia and Africa. And he has an active contributor to IPCC. So, Professor coordinating lead author in the chapter 12 and contributed the 6th assessment report. And he also advises the European Commission on Climate Change Research for Horizon Europe 2024 to 2027. So, Professor Dr. Roshankarana Singha, it's over to you.
Thank you, and good day. I'm feeling a little bit self-conscious after that extensive introduction, which you have taken from my homepage, I think. I'm just a little guy from Sri Lanka, okay, so I know a few things about climate change. So, first of all, I would like to thank Shiromani Jayawardena from the Climate Change Secretariat for introducing me to this, and then Professor Erandhati Lokupitia for inviting me to give this keynote speech. Thank you. Well, you heard a lot about me, but a little bit more of my previous life. So I grew up, I'm from Kandy. I grew up in Kandy. I went to school in Kandy, and then I went to University of Peradeniya, where I studied civil engineering during the troubled times in the late 80s. So yeah, after that then Australia for my PhD, and well, the rest is history, as they say. My substantive position is Professor of Climate Change Impacts and Coastal Risk at IHE Delft in the Netherlands. And I'm also a senior specialist at Deltaris. So these are all institutes, Dutch institutes that are doing a lot of research in the water area. That's my area of specialty, is water, anything related to water. Specifically, I'm a coastal engineer. So my area of expertise is looking at coastal hazards with or without climate change and what to do about it. And then I got involved in the IPCC process in the AR6, the recently concluded AR6. So in that I was a coordinating lead author in one chapter, and as a part of that, of course, you get pulled into other things like the summary of policymakers and other chapters. So the list of chapters I was involved in is given there. So to go on to my talk, let me see whether I can manipulate this thing. Okay. So you already heard a lot about climate change in the morning talks, but I always like to start a little bit with the bigger picture. So this figure that you see is the carbon dioxide levels in the atmosphere over about 500,000 years. And as you can see, so there's this cycle that the world has been experiencing where carbon dioxide levels go up and down and up and down, and roughly it happens it has a cycle length of about 130,000 years. Okay, so it's a natural process. It warms up due to various things, and then there's a big volcano or something. There's a lot of dust particles in there, and it cools down. So it's part of a natural cycle. So why are we then worried about this? Well, because of this. So since about 1850, it's gone up very much higher than it has ever been in the last 500,000 years. So the current levels of carbon dioxide in the atmosphere has not been reached for more than 650,000 years. So that's why we are worried about this. Now, as you probably know, one effect of increasing carbon dioxide levels, should I direct this at there or? Okay, is increasing temperatures. So these are the measured levels of temperatures since 1850. You can see it's flatlining at the beginning, and then since about 1840 or 1950s or so, it's really going up, right? So it's this is from different data sets, and all the data sets show that the temperature is really going up. As Professor Erandi mentioned earlier, so like the last 10 years has been the warmest on record. This can be also seen if you look at the probability distributions. Not timing, okay. It takes a little getting used to. So these are the probability distribution functions. I hope you know a little bit about statistics. So if you can do some probability analysis, you can see how since the 1880s till the 2010s, the probability distribution of temperature changes over land, over the ocean, and the world as a whole. You can see clearly in wherever you look, it's really increasing. Okay, so there's, as we say, unequivocal evidence that the temperature has been rising. On a personal level, I mean, you feel that, right? Even in Sri Lanka, I feel that I have been away for a long time, but every year I come back to Sri Lanka. I grew up in Kandy, as I told you, so I remember when I was going to school, when we used to go to play cricket in Asgiria, in the afternoon sessions, we always wore a jumper because it got cold. And in December, January, when you're going to school, it's so cold. We used to wear a jumper. But now, in Kandy, you hardly need to wear a jumper, ever. Maybe 1 or 2 days, but it's so warm. So you feel that on a personal level. Even in Colombo, you must be feeling that over the last 25, 30 years, it's really got warmer. So coming to the 6th assessment report that we concluded in 2021, it contains the same working group reports as the previous IPCC reports did. So we have working group 1 on physical science, which is what I was involved in, working group 2 on vulnerability and impacts and adaptation, and working group 3 on mitigation, and then bringing all things together in a synthesis report. It was quite disrupted by the whole COVID thing, so we had to do a lot of work online actually towards the latter part of the process, and as a result, things got delayed by about 6 months. So we launched the effort in June 2018 and released the first working group 1 report on August 9th, 2021, about 6 months after schedule. Working group 2 was released shortly afterwards, and so in the last synthesis report was released last year. So a lot of people ask that this is the 6th report of the IPCC, right? So a lot of people ask, so why do you guys keep doing it? What's new about it? There's working group 1, IPCC 1, 2, 3, 4, 5, so 6. What is new? Well, so therefore I have this slide. So I mean, there's a lot of things that are new about AR6. Every assessment report has some new components, but these are the main things that I think are the coolest things about the AR6. So because there's a lot more instrumental records and better models, we have unprecedented amount of attribution of hazards to climate change. Attribution means, so if there's a flood today, is it due to climate change? Do we see a climate change signal in it? Is it because of natural forces, or is it because of climate change? So there's a whole group now based in Europe that have developed very fast methods, statistical methods, to attribute certain hazards to climate change, like a big flood event or a heat wave or something. They can do this within 2 weeks. So in AR6, we have a lot more attribution of hazards to climate change. And for the first time, we present sea level rise projections up to 2300. The previous reports all stopped at 2100. So we go up to 2300, recognizing that some of the adaptation measures would require very long planning. Like in the Netherlands, where I am now, 1/3 of the country is below the mean sea level. And that's the most productive economic zone in the country. Of course, there are dike rings and rings of dikes. But if very high sea level rise happens, then they have to have plans. And you can imagine moving a city like The Hague. It cannot be done in 50 years or 100 years. It takes 200, 300 years to move such a city. So therefore, adaptation and also being prepared is also essential. So therefore, this kind of long projections, although there's a lot of uncertainty inherent in such projections, they are needed by some people. Then for the first time, IPCC always stopped with kind of global maps that are not really very useful for regional scale or local scale adaptation. So for the first time, we have a regional chapter, which is the one that I led, where we assess 33 climatic impact drivers in 51 regions of the world. So that's as granular as we can get in a thing like the IPCC. So we try to give more useful information that can be used for regional decision making, at least to identify hotspots. Also in the working group 1, we have extensive assessment of coastal climatic impact drivers, which were traditionally done on a case-by-case basis in the working group 2, but in working group 1 this time, we recognize things like relative sea level rise and coastal erosion and coastal flooding as globally relevant climatic impact drivers. And we have an interactive atlas. So in the previous reports, it was a paper atlas, but this time it's an interactive atlas. You can just get on it online and manipulate various things and see what is projected for your region of interest. So these are, I think, the key new things in AR6. AR7 has just started, so the whole cycle has started. Still, I think they haven't decided, or they just recently decided which are the reports that are going to be produced, but that'll be I think they're hoping to have the first working group 1 report of the AR7 out by 2029. They haven't started yet. Okay, so now to tell you about some of the assessments or projections we made in AR6. So first, I will talk a little bit about sea level rise, because that is relevant for everyone. Sri Lanka, especially being an island nation, it's really important for a country dependent on marine resources and tourism. So sea level rise is part of Chapter 9 of the AR6. Those are the authors involved. And one of the first things in that chapter that you will see is the history. So first we always look at the past, and then we go into the projection. So looking at all the data that's available, there's this high confidence statement in Chapter 9 that the global mean sea level has risen faster since 1900 than any prior century in at least the last 3,000 years. That's shown in this graph. You can see, so this is about 3,000 years on the x-axis. And this last bit that it goes up really high is since 1900. So before that, it goes up and down, and now it's really going up. So there's high confidence in IPCC means something. It is not just some authors thinking, oh, how confident are we? But high confidence means that there's evidence to say such a thing on multiple lines of evidence. So it'll be historical records, it'll be model results, it'll be attribution. So if many lines of evidence show the same thing, we will attribute high confidence to it. So looking at the numbers, then the global mean sea level rise, so if you globally average the sea level rise, in the last century, it's about 0.2 meters, 20 centimeters. You can say, well, that's not a lot. It's something like this, right? It's not a lot. But it does matter. So what is remarkable is that the rate of sea level rise is increasing. If you look at the first 70 years of the last century, the rate of sea level rise is 1.3 millimeters per year. And if you look at the last few years, last 15 years or so, it's almost 3 times that. So 1.3 meters, 3.7 meters. So it's really accelerating. So that's a cause for concern. And then, so we always do these assessments based on some pathways. So in the AR5, it was RCPs, reference concentration pathways. In the AR6, we use SSPs, shared socioeconomic pathways. So you will hear in my presentation a lot of these numbers. So here, oops, sorry. These are the 5 different scenarios that we looked at in AR6. This is the most optimistic scenario, SSP 1.9. So this is the carbon dioxide concentration, emission of carbon dioxide, yes. So according to this, if we were to follow this, we would have already started making very drastic cuts in carbon dioxide emissions and then reaching 0 by about 2050. Well, as you know, this hasn't happened, so that's very optimistic. In the next one is 2.6. Also, we would be starting to make rapid cuts now, continue to make cuts, and then we'll reach 0 around 2070. This is moderate, so 4.5, where we still keep emitting, getting higher a bit, and then start to cut down by about 2050. This is where we are on now. This is why we added this. This is the trajectory that we are on now, 370. And this one is a worst case scenario, 8.5. Recent research has indicated that because of the cuts that have been made already, not because of the pledges are yet to be made to fulfill, right? But because of the cuts that certain countries have made, it's unlikely that we will follow this trajectory. So that's already good news. Some progress has been made, because this is a terrible pathway. This would mean 5 degrees above pre-industrial level by end of this century. So that's bad news for a lot of things. Also, Professor Lokopedia mentioned, I was very glad to hear that about non-CO2 greenhouse gases. I always put these things like this methane and nitrous oxide. These are not getting a lot of traction yet from climate scientists, but these are really important greenhouse gases because they are long-lived. Carbon dioxide goes into the atmosphere, and it also can be taken out very fast. So if you cut emissions now, the instantaneous will be, the response will be almost instantaneous. But with things like methane and nitrous oxide, they live for a long time in the atmosphere. They cannot be taken out so easily once you put them onto the atmosphere. So those are going to become fairly important if measures are not taken. I understand in certain countries like New Zealand, where there's a lot of methane emissions because of livestock, certain measures are being taken. And nitrous oxide is something that's also resulting from a lot of building construction and things like that. So due to that, actually in the Netherlands, there have been recent limits placed on new building constructions. So that leads to other problems. So limits on building new house building then leads to a shortage of houses, and then the prices skyrocket. And then to negate that, then they have to put the interest rates up, and then the economy. It's all linked, right? So you do one thing, and 3 other things become impacted. But yes, things have to be prioritized. So just remember these scenarios. Now, with each of these scenarios, there's also a temperature at which the world will stabilize. So these figures are from the summary for policymakers. This figure is figure 4. And just look at the first bar plot here. So that indicates the temperature at which the world will stabilize if we were to follow each of those climate scenarios. You can see if we were to follow the track we are on now, SPM 370, we are going to end up at about 3.5 degrees more than pre-industrial. And the 1.5 would be here if you follow the 2.6 scenario. The dark bit in each of these bars is where we are at now. On average, it's about 1.1 degrees more than pre-industrial. That's where we are now. So that's just to give you an idea of the background of the assessment or the boundary conditions. Now, the sea level projections. So first we have a figure that gives the sea level rise up to 2100 like the previous projections. So in this figure, note that everything is relative to 1900, although the figure goes from only 1950. So we have the 5 scenarios. The solid line is the median estimate. And so if you want to reduce it to a more recent baseline, like 1995, 2014, like here, then you have to subtract 0.16 from the figure, from the values given in this figure. So you end up with the higher scenarios of something around 1 meter. 1 meter of sea level rise by the end of this century compared to the beginning of this century. Again, 1 meter is, well, see about here. Okay. So you might think not a lot, but I will tell you why it is actually quite a lot. But before I do go there, I also want to draw your attention because a lot of people do use this dotted line. That's the new thing. Okay, the previous reports didn't have this. So a lot of people think that this is another scenario, but it is not. It is actually a storyline. So what we call it a low likelihood, high impact storyline. It's different to a scenario. A scenario is a plausible future. Okay, it's something that is deemed to be possible. This is just a storyline, which means you under certain assumptions, if certain things happen, that can eventuate. It was added to help being prepared. Personally, in the discussions that happen in IPCC, behind those, I was personally against putting that line, dash line, because I thought people look at graphs, they see a line, they say, okay, this is the top scenario, and that's all they see, right? Most people don't read the fine print around it. So if you read the fine print, you will know that this is a very, very extreme situation that can happen only under certain situations, and those are actually highlighted in the text. So for that dotted line to happen, first of all, you need to have very strong warming. So SSP 58.5 is a necessity. That's a basic condition for that storyline. And then you need to have faster than projected disintegration of the ice shelves in Antarctica. And then you also have to have larger than projected mass loss in Greenland. So all these things have to be satisfied for that line to happen. So it's a very low likelihood, but a very high impact storyline. You can consider it, but there's a lot of uncertainty around it. Okay, so I just want to highlight that because that dotted line is there. IPCC is a very consensus-based process, so I was completely outvoted in not adding this line. Now, to 2300, I also mentioned that we provide some projections of 2300. There's a lot more in the text than what I'm showing in the graphs, so these are now plotted on the same axis to make them comparable. So this is the previous graph I showed you, and it's the same vertical axis. You can see by 2300, even under a low emission scenario, you are projected to reach about 3 meters of sea level rise. And with the high scenario, this is 58.5, it's about 7 meters. 7 meters. Okay? That's about, I don't know, I see a lot of middle-aged people here. Like when I was studying, we were using still the, what do you call that? The feet and inches system. So yeah, for me, I don't know, still it's easier to understand units in those terms. So 7 meters is 21 feet roughly. That's pretty high. But it also gets worse. If you consider that low likelihood, high impact scenario, we have this very carefully constructed sentence saying that sea level rise exceeding 15 meters cannot be ruled out when deeply uncertain processes are taken into account. 15 meters. Okay? 45 feet. But there's a lot of uncertainty about it. Then, interestingly, about sea level rise, the other thing is it is not like precipitation, winds, temperature. Because 70% of our world is sea, right? Is water. So there's a lot of hysteresis in the whole sea level rise process. Even if we stop emitting greenhouse gases today, even if we bring down the temperatures very, very fast, sea level rise will continue for centuries or thousands of years because there's a huge lag in the process. So then we have what is called committed sea level rise. So this figure shows the committed sea level rise for two situations. One is if the world stabilizes around 2 degrees more than pre-industrial, and the other is if the world stabilizes around 3 degrees above pre-industrial. So then in this scenario, with 2 degrees, there's a 2,000-year commitment that the sea level rise will be between 2 meters and 6 meters. So there's always uncertainty, but there's a committed sea level rise of between 2 meters and 6 meters over a 2,000-year period. Over a 10,000-year period, there'll be a sea level rise of 8 meters to 13 meters. And you can see in the +3 scenario, it's much higher. Okay? So we want to stress that because of this committed sea level rise thing, that sea level rise is not a matter of if, it's a matter of when. It will happen no matter what we do now. So while we are mitigating, we will also have to adapt, especially island nations like Sri Lanka and even more the small island states that have very limited adaptive capacity. Sea level rise will go up over time. So unless you are planning to evacuate the country in a couple of thousand years, then something has to be done if you want to keep living in those areas. Okay, then I told you why a sea level rise of 1 meter even is important. So if you drive down from Colombo to Galle, and if you notice those signs with Hikkaduwa or Mount Lavinia, the Hivela, every place there's a sign, right, saying this is the area name, and there's at the bottom in small print there's elevation above mean sea level. Notice it next time when you go down to Galle, if you take the main road, not the highway. And if you notice it, most places that elevation is less than 1 meter above mean sea level. Less than 1 meter. So just with sea level rise by 2100, that will be underwater. But what matters to be able to live in the coastline is not have periodic flooding. And periodic flooding is caused by what we call extreme sea levels. Extreme sea levels is the addition of all these things that you see there. So sea level rise is one component, but then top of that you have tide, storm surge, and wave setup. Now just back of the envelope calculation, so let's assume a sea level rise of 1 meter. We are already here. Tidal range is about, I think, 0.5 meters in Sri Lanka. So let's add half of that, 0.25. So 1.25. Storm surge, 100-year event could be about 1 meter. So 2.25. Wave setup can be about 20% of the offshore wave height. So if you get a big wave event of 2 meters, that also adds about half a meter. So you are getting pretty close to more than 2 meters. That's, over me. So if I'm on the Galle Road, when something like that happens, it's like a mini tsunami. And then imagine this happening every month. That's what sea level rise does. For extreme sea levels, the frequency is really increased a lot. I will get into that a bit later. So if that happens so often, there are some places on the US East Coast now where they call it nuisance flooding. So every month during high tide, there's some flooding on the road. People can't go to work. Kids can't go to school. That's nuisance flooding. So what do? Either you build a dike or you move up. And this is already happening. So that's why adaptation is really necessary, and it takes a long time to do these things. So one of the main things we find in the IPCC report, both in Chapter 9 and Chapter 12, and summary for policymakers, is that the global mean sea level rise is projected to turn what today is an extreme sea level event that has a return period of 100 years. So today, according to what has happened in the past, an event that has a 100-year return period, I'm sorry I have to assume that you know what return period event is. So it's an event that has a chance of happening once in 100 years. Okay. So event that has that return period is turned into an event that would happen multiple times a year. So that's what I mentioned. Like if, let's say, a 1.5 meter extreme sea level event that only has a chance of 1 in 100 that's happening today. By 2100, that's going to happen multiple times a year. So that's going to make some areas unlivable without adaptation. Now, some projections that we got for Sri Lanka from a different project. This is not IPCC, this was after IPCC. So we looked at the 100-year return period extreme sea level at different global warming levels around Sri Lanka. We only show some results in some places. So you can see here. Well, now I need my glasses. Or do I? I can't read the scale, unfortunately. So dark green is about 0.5 meters and red is about 4.5-5 meters. So you can see at present, all around Sri Lanka, the 1 in 100-year extreme sea level event is around 0.5 meters. It's not a lot. So that's at present, okay, without sea level rise. And you see 3 dots. So that's the middle one is the best case scenario, and the top one is the worst case. So the middle one is the central estimate. So it's like the median, and this is the worst case, and this is the best case. So that's today. If we look at a 1.5 degree warming scenario, you can see already the higher estimate is getting yellow. So it's like 1.5 meters all around the country. And if you go to 3 degrees and 5 degrees, you can see that again the top estimate turning darker yellow and even getting red towards the 3 degrees. So here we are reaching about 4 meters of extreme sea level for a 100-year event all around the country. Okay, so if you look at these, you can look at this in detailed way. I put this here, but I realize this is too complicated to explain here now. This is basically all the different warming levels we looked at for different locations, how that you can see it's only going up. Okay, this is the higher estimate and the central estimate. But the main conclusions were that extreme sea levels all around Sri Lanka will increase by 60 to 200% under 1.5 degrees of warming, so up to doubling, and up to about 2.5 times more under 3 degrees warming, and up to 4 times more under 5 degrees of warming, all around Sri Lanka. And the increases in the extreme sea levels, especially the upper estimates, are higher along the east coast and along the north coast of Sri Lanka than in other parts of the country. So we also are we are finalizing now a coastal flooding estimate. That's a global flooding estimate, so it's pretty close. But of course, because I have interest in Sri Lanka, I look closely at the results that we get for Sri Lanka. And following up with this, it shows higher flooding along the east coast of Sri Lanka mostly. And yeah, the increase in extreme sea will become very highly pronounced for warming levels more than 3 degrees. And yeah, that's it for that study. Okay. So now I move on to climatic impact drivers, which is in the chapter that I was coordinating, in chapter 12. Again, those are all the authors involved in it. There's 50 more contributing authors that contributed to it that I didn't have space to put there. So what is a climatic impact driver and why did we define it? So, okay, first the definition. It's a long definition. It's basically a physical climate system condition. It could be a mean value or an event or extreme that will affect an element of society or ecosystems. Now, why did we come up with this term is because the IPCC report goes through a number of reviews. Okay? It's open for review by people and experts. Every time we produce a draft, we put it out there and announce it, and anybody who wants to comment can comment. And we as authors, unlike in a journal, in a journal paper, when you get comments, you can choose also to not respond to it. But at IPCC, we are compelled to. We had to respond to every single comment. I think in Working Group 1 report only, we had like 75,000 comments that we had to respond to. There's a huge Excel sheet, and we had to respond to it. So in the first draft that we put out, a lot of comments were made that why is, we call them these things like, mean temperature rise and heat extremes and flooding, we call them hazards, like they have called in earlier reports. They are hazards. But then there were a lot of comments saying, why is IPCC so negative? Everything is a hazard, everything is bad, but some good things can also happen from climate change. So why don't you use a neutral term? So then we came up with this climatic impact driver. So it's an impact driver. It's a driver of impacts, which is of climatic origin. So there are many other impact drivers also, like an earthquake or socioeconomic development or COVID-19. Those are all driving impacts, right? But they are not climatic. So IPCC is not interested in those. IPCC is interested only in impact drivers that are of a climatic origin. So hence, climatic impact driver, or CID for short. So then we identified 33 different climatic impact drivers. These are derived after a lot of work. So they are based on the essential climate variables, which the meteorologist and hydrologist here would know about. And then we also try to link them to the Sendai Disaster Management Network framework. So based on all that, we came up with 33 climatic impact drivers in 7 categories. So the first is heat and cold. In that you see things like mean air temperature, cold spells, frost. Then there's wet and dry. There we have things like river flooding, mean precipitation, landslides, aridity. Then we have a wind category, snow and ice, and then coastal, oceanic, and then some other. Okay. So I'm not going to go through all of them, but these are the 33 different climatic impact drivers that are measurable and are used in the world today in different sectors with specific indices so that we can track them. They are not qualitative, they are quantitative. So we needed these to be quantitative. And these are then also linked to the different sectors that are assessed in the Working Group 2 report. Working Group 2 report deals with these 8 sectors, so like cities and health and water, ocean and coastal ecosystems. So each of these climatic impact drivers are linked to those sectors. So here is just one example that I put there, and here what this shows is if there's a high relevance of a climatic impact driver to a certain asset in a certain sector, then you have this orange color. If there's a low relevance, then you have white color. So this is, I think, food and fiber sector. You can see, fairly high relevance for the crop systems here, for example, with all the most of the wet and dry climatic impact drivers, right? So they are all linked like that. So the CIDs are linked to the sectors assessed in Working Group 2. Then we provide in Chapter 12 observations and projections of the direction and magnitudes of change for each CID in each IPCC AR6 region. So as I mentioned, in AR6 we subdivided the world into these regions. So land regions and oceanic regions, so 44 regions altogether on the land. And then we, in our chapter, in section 4, 12.4, we provide all the regional information on changing climate on a continental basis, and also some special zones, so like Africa, Asia, and then small islands, polar regions like that, for each of these regions. We have sets of global maps, like previous reports, for different timelines. So I think mid-century and end century, and also for a low scenario and a high scenario. So you can see here is 2.6, here is 8.5 in the future. This is mid-century. And these projections are for days with temperature more than 31 degrees. And the second one is heat index. I see that in Sri Lanka now the Met Department puts out warnings for heat stress. So this is using the NOAA heat index. So days that are more than 41 degrees on the heat index. how that changes. You can see it's all going in the wrong direction, right? And this is droughts, this is soil moisture, this is change in wind speed, and this is extreme sea levels. So yeah, I will not explain this, but just to tell you that these are there in the chapter. You can have a look. And then for each of the continents, we also produce, on top of those 6 CIDs that we have mapped in world maps, we produce some more specific information that we didn't put in the world map. So here for Asia, we have the 100-year return period stream flow by 2050 and 2100, and there we have a little bit more information, a bigger figure, and also the uncertainty bands for warming levels and scenarios for each of the different regions in Asia. Okay, so these are all like East Central Asia and South Asia, Southeast Asia. So for each of those regions, you have this uncertainty plot, because you have to recognize that there is uncertainty. In each of these lines, there is a dot. That's the median value. But the whiskers line and the whiskers, that shows the uncertainty in the projection. So if you really want to do a risk assessment, then you have to cover the full range of possibilities. Just taking the median might not be enough. Okay? Now, one of the main products of our chapter is what we call CID tables. So CID tables show the confidence in direction of change by mid-century. Direction of change, okay, not magnitudes. We are not talking about magnitudes, only how it can increase or decrease, and then relate it with a confidence statement. So how to read this is so this is the table for Africa. So here we have a map of all the subregions in the continent of Africa, and then these are the different subregions. These are the 33 CIDs, and if it is red, that means we have high confidence of increase by 2050. If it is dark blue, that means we have a high confidence of decrease by 2050. So you can see here the mean temperature and the extreme, the heat is, we have high confidence that it will increase by mid-century. And then all the coastal and ocean CIDs, like relative sea level rise, coastal flooding, coastal erosion, acidity, mean marine heat waves, all those, we have high confidence that they will increase by 2050. So this was like to synthesize all the things that we reviewed, and a lot of work went into this. So we produced a table like this for every continent. Now we are in Asia, so let's look at Asia. You can see in Asia also, the temperature CIDs are projected to increase with high confidence, and also the coastal CIDs. So these ones are increasing everywhere, the red, and then the cold ones are decreasing everywhere. Also extreme precipitation is increasing everywhere, and then the coastal CIDs are increasing everywhere. If you want to look at the regions that are, well, let's say most at risk, then you can look horizontally. So that's where the green boxes come up. The regions shown by the green boxes are the regions in Asia where most CIDs are expected or projected to increase or decrease. So the most count of dark red or dark blue. So that's West Central Asia. You can read the list: Russian Far East, East Asia, and South Asia. If you specifically look at South Asia, then again you can see the same trend. So mean temperature, extreme heat are increasing, and all the coastal CIDs are increasing. This is probably not very relevant for Sri Lanka, but for some parts like Tibet and East Central Asia, it's relevant, all the snow and ice ones. And extreme precipitation. So that's how you can look at a region that you are interested in. But still, you can see that's a fairly large region, right? South Asia is large. So you can get indications of what are expected to happen in your region, but you can't use those really for adaptation measures, because for adaptation measures you need more local information. So anyway, what does this mean for Sri Lanka, implications of Sri Lanka? So based on the global data products that we assessed for IPCC and also some downscale results, but still that would be limited to codex, which is 50, 60 kilometers resolution. So based on that, we have high confidence that mean temperature, extreme heat, mean and extreme precipitation, pluvial flooding, and all the coastal CREs will increase by mid-century. And so then the impacts like heat stress, inland and coastal flooding, energy consumption for cooling, shoreline retreat may all increase. Agriculture, fisheries, coastal ecosystems may be negatively impacted, but because extreme sea level and mean precipitation is projected to increase at that scale, you could think hydropower generation could increase, but this needs further research. So something I see as a need for Sri Lanka is I'm aware of what the local authorities are doing in terms of developing more detailed analysis, like Mr. Randeni was mentioning today earlier in the morning. But based on what I know, I think something that is really needed to inform specific adaptation measures for specific sectors and for specific areas of the country, not at the country as a whole. You know, adaptation has to be done always at a local scale. So it has to be a certain stretch of the coast along the southern provinces, or certain district, or it's very small. These are not captured in one grid of the models that we are using. Okay, the GCM, the Global Climate Model grids are like 100 kilometers. So you can imagine Sri Lanka is like covered in 4 cells. You can't get anything reasonable from that. Even downscaling, most downscale models are like 50 kilometers. You have 9, 10 cells. For statistical significance, you need 30 numbers at least. So mathematicians here would know, right? So, but importantly, Sri Lanka, the climate of Sri Lanka is governed by the monsoons, right? You know that. The monsoons are very, very important. So it is necessary to get high-resolution projections that actually capture the monsoon signal. I have looked personally with some students at some of the like codex results or 50-kilometer downscale results, and some of them do not even capture the monsoon signal. You plot the precipitation for the whole year, it's like this. But you need to see 2 peaks, right? That is not captured. So if that is not captured, then how can you trust all the numbers that are coming out of that? Right? So I think it's very important to do extremely careful model selection. Only pick the models. So there's no point. There's also widespread belief that, well, you take 35 models and you average it and you get a robust ensemble. No. Only if the relevant features are captured, right? So it's better to have 7 or 8 models that actually capture the monsoon signal and then use those for projections. We have started looking at this. Shiromani is helping me with that a little bit. So we are looking at this in collaboration with the Institute of Theoretical Physics in Trieste, Italy. And yeah, we're getting some preliminary results that are showing interesting things. But yeah, maybe in the next conference I can present that information. So yeah, that's important to do careful model selection that capture the important features of the climate. And then once you do those reliable downscaling efforts, I think from what I have seen, even resolution of more than 25 kilometers will be required. Until you go down 25 kilometers, there's no hope of catching the monsoons. So once you have that, then to inform the local scale adaptation, like I mentioned, like in certain part of the country, then you need to have very detailed impact models. So for example, to have a flood mitigation effort. For flood mitigation, what do you need to do? Either you need to build a nature-based solution, which is how long? 1, 2 kilometers, 5 kilometers? Right? That's very small. So then you need to do a detailed impact model with really high resolution, like 10 meter or 20 meter grid sizes. And or for shoreline change, we need to do at least 500 meters because each beach can be different, right? But these can be then simulated with confidence using the projections of those more robust downscale projections. And then we can come up with a plan. Okay, we need a seawall this big, or we need a sand nourishment this big, or we need to turn the rivers from the south to the north. But we need to first have done this robust, careful model selection, and then the impact assessment. Unless you do it like that, it's very difficult to get climate financing. By saying things like Sri Lanka is in the top 25 countries for climate change impacts, the World Bank or the ADB is not going to give funding for that, because this money is not just lying there in an account. This is from taxpayer. This is all from taxpayers. Right? Everybody who goes to work on a bicycle in sub-zero temperatures pays tax. People who are earning less than you, maybe, right? It's their money that is dispersed to do these things. So these organizations are extremely strict on accountability. So unless you do a very robust assessment on climate change impacts, adaptation, and show that it's a bankable project, the funding will not come easily. Just by saying Sri Lanka needs money, it's not going to come. You have to have detailed local solutions worked out, and then funding will come with accountability. I have been contacted many times by these organizations to do assessments of reports that have been produced to finance such projects. And I mean, I'm really, every time, super impressed by the level of detail that the consultants have gone to do this analysis. Really precise. Coming back to IPCC, there are some other resources other than the chapters. So there are 12 chapters, and then for people who don't want to read the long report, there's the summary for policymakers, which is about 10-15 pages. There's also a summary for all, which is written in a non-technical language. So that's easy to read for people who don't want to read the scientific jargon. The links are given there. And then I mentioned the interactive atlas. So this is also freely available at that website. You can go there and click on, so this is on regional basis. So you will have to look at South Asia for Sri Lanka, and then you can look at, you can change things around for global warming level or scenario and time horizon and see what is projected. The coastal climatic impact drivers were not included in the atlas, so we have made this separate viewer for coastal stuff. So like regional sea level change, extreme sea level coastal flooding, and extreme waves. This is hosted by my organization. All the data products that were used in the IPCC report, and also some data products that became available later in this. You can navigate through it easily. If you have any questions about this, you can feel free to contact me. There's also an info button. So to wrap up, then again, with all this bad news, there's also some good news. So where do we end up with the current government pledges for emission reduction? As Professor Lokopedia mentioned earlier about the 1.5 degree warming target of the Paris Agreement. So this figure is an assessment done by 3 different organizations. Here is the temperature levels we will come up to with the different SSPs. Okay? And with the current policies, this is what the three organizations came up with. With the current policies, we are going to end up around 2.5 degrees of warming. So with this moderate scenario, okay, that's what, if the current policies are adhered to, that's where we'll probably end up at. If the 2030 commitments are also honored, then still we are around that mark. If the net zero pledges that have been made in the COP meetings will probably come closer to 1.5, but these are pledges, okay? So they have to be honored. It remains to be seen whether they will be honored. So, yeah, if it all goes well, we might save ourselves from destruction. So that's good news, I think. And so I end with this. This is basically from the presentation that came out with the release of the report. So climate change is already affecting every region on Earth in many ways, and the changes we experience will increase with every fraction of future warming. So 1 degree or 0.5 degree, or it all matters. Things change. A lot of things change with every fraction of change. So I think I will end it there. Thank you for your attention. we have question session or do I have open? So apparently I can answer some questions. Please, maybe one of you can moderate, Tonsilu.
Hello, sir. This is Ghanshyam Sharma from India. I wanted to know about hydropower. How is it helping to increase? Because I'm from the Himalayas, and almost all the parts of Himalayan rivers are under hydropower generation. And I think the contribution will be enormous in the days to come. So can you enlighten on this? Thank you.
I can cautiously comment on that because I haven't been involved in any downscaling studies, as I mentioned. But yeah, according to what we see, of course, when you say Himalaya region, so there's going to be a widespread melt of the glaciers, of the ice there. So of course, your river flow is common sense that it will increase. By how much is something that has to be assessed through detailed modeling. But yes, I think there will be, and also the projections show increases in mean precipitation, as well as the extreme precipitation, and on top of that you have the ice melt from the Himalayas, so yes, you will have a lot of potential for hydropower generation in the future, and it probably already happening now, I think. Yes.
Hello sir, this is Dr. Kakuli Banerjee from Central University of Odisha, India. I am working on biodiversity and climate change. I just wanted to know whether IPCC has any record on the, you might be having, you have already shown the shoreline changes. In Odisha, you might be knowing that it's a hub of cyclones, the most, but it doesn't have any sea level rise effects. But there is a shoreline change, and there is a landward shifting of the mangroves. So what do you think in the near future? Is there any projections that has been framed by IPCC that in the near future of 50 years or 70 years or 80 years, there will be a huge loss of mangroves, because that is the only shelter bed which we have for the coastal disasters. So if you can throw some light on that.
Okay, good question. Mangroves are usually on muddy coastlines, right? Yeah, so when we were doing the IPCC assessment, we tried to be, at least in working group 1, we try to maintain some consistency in the whole world. So we look at data sets that cover the whole world, not specific areas. Working group 2, which I was not involved in, looks more on a side-by-side basis, case studies. Working group 2 has a lot more case studies, which you may find for Odisha. In working group 1, because of our global consistency preference, we looked at projections only for sandy coastlines. So those are given also for India, also for Sri Lanka, globally, but using one method in one paper published in Nature Climate Change. So those could be useful. But for mangroves, I think it's a little bit more complicated than that. But no, I can't give a good answer. But maybe you can contact NIO. They are doing a lot of work on that. No, also the NCCR. I am in contact with these people, Dr. Ramana Murthy. Yeah. So maybe they have. But also in India, they produced. I think again from NCCR, they recently produced a national shoreline change projection, a report. Maybe they took into account the mangrove shorelines there.
Not exactly, actually, they have worked basically only on the shoreline changes.
Only on the sandy shorelines?
Yeah, not only sandy, it has taken the shoreline as a whole.
Okay.
Because as you are saying, we already have in Sundarbans, we have a sea level rise, because it's a funnel-shaped shoreline part. So we have already a sea level rise, huge sea level rise there. So in that case, what we have been seeing that there is no recession of the mangroves as such in Sundarbans. But in the western West Bengal, from the Odisha coast, we are having the recessions, and the mangroves are dying out. That is a very alarming situation, and there is a natural phenomenon which is happening. So
but why are the mangroves then? The mangroves are dying because of some biological reason, right?
Maybe, but it's a very typical phenomenon which if you go through because I have been working on the coast. So I have seen, because I was working with a project for the Ministry of Earth Sciences, Government of India on the same.
Okay.
So there we have found that the northern part of the mangrove belt is basically, they are telling that is because of the huge salinity intrusion, the
Yeah.
water which is coming out. So that is making the physiological process of the mangroves, it's in a very salty state. So because of which the osmotic regulation which is taking place might be, it's in a very higher hyper level. So because of which there's internal dying. So it's becoming black, dark in color. And slowly it's dying out.
Yeah.
It's becoming lean and thin and dying out. So it's a very alarming situation for Odisha.
Yeah.
So a lot of research needs to be done. So I would like to highlight here in the forum that these studies, I think it should be one of the major important components where we should focus now, because mangroves are the only shelters that we have in the coastal zones from natural disasters.
Yeah, but so you already know the reasons then, because of hypersalinity and things like
Yeah.
that. So these are also things that we don't know yet. I also see in Europe, it's almost become fashionable to talk about nature-based solutions, Professor Lokopitia mentioned. But there are things that we don't know about how sustainable these are in the future. You saw in the projections that the ocean acidity is going to increase everywhere. There's going to be more marine heat waves. So how feasible would these mangrove reforestation projects will be in the future is a bit unknown.
Yeah, and it's a big challenge for the whole country, the whole world.
Yeah. Okay, good point.
Yeah.
Thank you.
Thank you, sir.
Hello, sir. My name is Apurv Ashish. I'm from Birla Institute of Technology, Meshra, India. So I'm
from where,
working Birla Institute of Technology. I'm an assistant professor at Birla Institute of Technology, Meshra, Ranchi, India. So I'm actually working on improving the energy efficiency of buildings with a multi-objective optimization framework. So are there, in these 13 CIDs that you talked about, do we have anything related to these CIDs, particularly related to the building industry, that I can basically use in my framework?
To the building industry?
Yeah.
Yeah. I mean, definitely in terms of cooling and heating, right?
You said that there are indicators that, that are connected to the sea level rise. So building industry being almost 40%, the big contributors to CO2 as well as, these greenhouse gas emissions. So building industry is a rather very big, it has a very big component of, say temperature rise in India, Sri Lanka, or any other place that we are talking about. So.
Yeah, for sure. Like I also said, there will have to be, I think, limits made on building industry. If not to fight climate change, also for this air pollution problem, which is a completely different problem, right? You can see already in Colombo, there's a lot of air pollution. You can feel it. And in places like Thailand and in Bangkok and Hanoi, they are closing schools. So building industry is a contributor, yeah, but because of the long-lived forces like nitrous oxide, so yeah, that will have to be limited. But when you ask about CIDs that are related to the building industry, I think there is also a sector in Working Group 2 that's on the built environment. So there will be connections made on various CIDs. It's not at the top of my mind now, but if you look at that table, I think 12.2, you will see the connections between the different CIDs and that sector and the asset class.
Okay, thank you, sir.
You're welcome. So I'm getting questions only from Indians, not from many Sri Lankans. Anybody from online, maybe? Nobody's asking questions online? Okay. Okay, well then if that is all, then I'll be happy to talk to you on an individual basis later on. I'll be around for the 2 days. Okay, thank you.
Thank you very much for that amazing talk, and we are honored to have you at ICC 2024. Now it's time to deliver the special token of appreciation to Professor Rushankarana Singha. For that, I would like to invite our conference chair, Professor Erandati Lakupitiya, and our Managing Director and Co-founder of TIKM, Mr. Isankapi Gamage, to deliver the special token of appreciation to Professor Rushankarana Singha. Ladies and gentlemen, the special token of appreciation goes to Professor Rushankarana Singha to his valuable time and effort for the 8th International Conference on Climate Change 2024. Ladies and gentlemen, there's a slight change in the program. So now we are having the lunch break. So you can have the lunch in the main restaurant in the downstairs. And don't forget to be connected with your colleagues. And we kindly request you all to be seated by 1 p.m. We will be having the plenary speech after the lunch. Thank you.